What is post-quantum cryptography? Post-quantum cryptography, or PQC, protects digital information from quantum computer attacks. It replaces current encryption methods that quantum algorithms could break. In simple terms, PQC is about building encryption that stays secure against both classical and quantum computers. Why do we need new cryptography for the quantum era? Quantum computers can solve certain math problems much faster than classical computers. That's a problem because today's encryption depends on problems that are intentionally hard to solve. Algorithms like Shor's can break the foundations of RSA and elliptic-curve cryptography. That means attackers could decrypt private data or forge digital signatures. Symmetric encryption like AES-256 can be made stronger with larger keys, but public key cryptography can't just scale up. That's why new methods are being built from the ground up. Governments and standards bodies are already preparing. NIST has finalized its first set of PQC standards. The NSA and CISA are also guiding organizations to start migrating now. What makes post-quantum algorithms different? Classical cryptography relies on factoring and discrete logarithms. PQC uses entirely different math, like lattices, hashes, and error-correcting codes that are hard for both classical and quantum computers to solve. Post-quantum algorithms aren't quantum themselves. They run on the same classical computers we use today. That's why deployment can start now. The goal is dual resistance, security that holds up now and in a quantum future. What types of algorithms make up post-quantum cryptography? PQC includes several families of algorithms, each built on a different hard mathematical problem. The main ones are lattice-based, hash-based, code-based, multivariate, and isogeny-based cryptography. Lattice-based cryptography builds on geometric problems in high-dimensional lattices. Algorithms like Kyber and Dilithium form the foundation of NIST's standards. Hash-based cryptography uses one-way hash functions for secure signatures. Sphinx Plus is the main example, simple and proven over decades. Code-based cryptography relies on error-correcting codes. Classic Michaelis is the best-known system and has resisted attacks for over 40 years. Multivariate cryptography uses polynomial equations over finite fields. It's flexible but still being evaluated for wider adoption. Isogeny-based cryptography uses relationships between elliptic curves. It was once promising for lightweight key exchange, but is now under review due to discovered vulnerabilities. Which algorithms did NIST standardize, and what do they do? The National Institute of Standards and Technology selected 3 algorithms for global adoption: CRYSTALS-Kyber, CRYSTALS-Dilithium, and Sphinx Plus. Kyber is a key establishment mechanism. It secures key exchanges efficiently. Dilithium is used for digital signatures. It authenticates software, firmware, and communications. Sphinx Plus is a hash-based signature system. It's slower but extremely conservative, relying only on proven hash functions. Other candidates, like Bike, Classic Michaelis, and HQC, are still under NIST review to add diversity and backup options. How does PQC fit into real-world systems today? PQC is already moving from research to deployment. Organizations are testing hybrid cryptography, where classical and post-quantum algorithms run together. Hybrid systems let organizations stay compatible while adding quantum resistance. Migration is complex. Public key infrastructures, certificates, and trust chains all need updating. That's why crypto agility, the ability to change algorithms easily, is critical. Major vendors, including browser and cloud providers, are already testing PQC integration. The shift has started. How to get quantum ready in 5 steps. Step 1. Inventory your cryptographic assets. Find where and how encryption is used across your systems. Step 2. Prioritize long-lived and sensitive data, the information that needs to stay secure for decades. Step 3. Plan hybrid and phased rollouts. Test PQC alongside current encryption. Step 4. Build crypto agility into new architectures. Make it easy to replace algorithms as standards evolve. Step 5. Coordinate across vendors and ecosystems. Quantum migration will take years, and requires collaboration across supply chains. How is PQC different from quantum cryptography? PQC runs on classical computers and uses math for security. Quantum cryptography, like quantum key distribution, relies on physics and requires special hardware. Quantum key distribution uses photons to exchange keys securely, but isn't scalable across the internet. PQC, on the other hand, works everywhere. What's next for post-quantum cryptography? The first PQC standards are finalized, but more are coming. Adoption is accelerating across hardware, browsers, and operating systems. The long-term goal is a fully quantum-resilient ecosystem, one that's crypto-agile and standardized across all systems. In short, post-quantum cryptography is how we keep our data safe today and tomorrow.